This rotating supermassive black hole represents an extreme boundary condition in physics. At its center is the event horizon, a mathematically defined topological boundary where the local escape velocity exactly matches the speed of light. The film Interstellar explores the extremes of this boundary, placing a crew on an ocean planet, where 1 hour of local time equates to 7 years passing back on Earth. For that scenario to be physically possible, the required time dilation factor, represented as gamma, must reach approximately 60,000. A stationary Schwarzschild black hole cannot generate this effect, because its innermost stable circular orbit sits at 3 times the Schwarzschild radius. The distance is too great to create such a massive dilation factor. Reaching a gamma of 60,000 requires a Kerr black hole rotating at near maximum theoretical limits. This extreme spin drags the stable orbit flush against the event horizon. Riding this stable orbit creates a massive temporal divergence relative to the rest of the galaxy, though moving past the horizon replaces time dilation with physical destruction. Measuring this divergence requires a split in relativity between proper time, the experience of the person falling, and coordinate time, which is what a distant observer records. These equations define the relationship between coordinate time, delta lowercase t, and proper time, delta uppercase t. As calculated below, near a black hole 10 times our sun's mass, 24 hours of proper time equals 25.3 hours on Earth. To reach this extreme dilation, the black hole uses frame dragging. These formulas for spin parameter A show how a massive body drags spacetime itself. The effect is absolute. Even photons are forced to rotate with the black hole inside the stationary limit. While time dilation is a symptom of this warped geometry, the true danger lies in how that geometry physically interacts with human biology. According to the equivalence principle, a person in free fall should feel weightless because there is no local force of gravity pushing back against them. That principle only applies in a uniform gravitational field. Near a black hole, the field is radically non-uniform. This creates tidal acceleration, the difference in gravitational pull across the length of a single object, such as the 2-meter span of a human body. This document compares the force acting on the feet, formula F1, against the force on the head, F2. While this difference is negligible on the surface of the Earth, the scenario inside a black hole is terminal. Because the feet are closer to the mass than the head, they are pulled in faster. Simultaneously, the body is squeezed laterally as the angles of fall converge toward the center. This results in spaghettification, a simultaneous lengthwise stretching and sideways squashing. Spaghettification is not a trope. It is a mechanical failure of the body caused by radical gravitational gradients. We can calculate the exact spatial point where this acceleration exceeds the structural integrity of the human body. The formula for tidal acceleration is delta A equals 2gmd over r cubed. Look at the variables, m for mass and r for distance. Because of this relationship, tidal acceleration scales inversely with the square of the black hole's mass. If we assume fatal structural failure occurs at 100 Gs, we can calculate the kill radius for a stellar black hole of 3 solar masses. In this case, the human body is torn apart at approximately 1,200 kilometers from the center. This means death occurs 130 times further out than the actual event horizon. If we apply this same math to a supermassive black hole containing 3 billion solar masses, the results change. Because of the inverse square scaling, the tidal forces at the horizon of a supermassive black hole are 1,000 times weaker than the gravity we feel on Earth. This unique gravitational geometry creates an incredible loophole, allowing for a completely smooth, painless crossing of the black hole's event horizon. However, surviving the horizon is a false victory. The lethal tidal forces still exist. They are simply waiting deeper inside the topological trap. To an observer on Earth, an astronaut falling into a black hole appears to slow down and freeze at the horizon, eventually fading away. From the astronaut's perspective, the crossing is finite and terrifyingly brief. This reveals a common misconception. You won't see the universe's future play out in fast forward. Light from the future lacks the time to reach you before you strike the singularity. Seeing the future would require you to hover just above the horizon using infinite thrust, rather than fall through it. This plot shows how redshift scales with the impact parameter for a spinning black hole. Even when the spin is pushed to extreme limits, the downward slope confirms that a falling trajectory denies you a fast-forward view of the universe. The universe doesn't offer a final cosmic show. The optical reality is completely isolating and dark. The visual experience is governed by relativistic beaming and aberration. Extreme velocity causes incoming starlight to be shifted and bent forward in your direction of motion. The visible universe compresses into a shrinking, blue-shifted ring of light suspended directly overhead. Outside of that ring, your entire field of view is filled by a featureless, pitch-black void. Inside the horizon, space and time swap roles. The radial dimension becomes time-like, meaning all possible directional paths now lead inward. Escape is physically impossible. Firing a jetpack away from the singularity only increases your velocity through spacetime, causing you to arrive at the center faster. The singularity isn't a place in front of you, it's a fixed moment in your future. This single blinding dot represents the absolute final light reaching your eyes before the complete and total collapse. The finality of the singularity is the terminal result of a collapsing spacetime topology.